introduce to Mr. Shomo. So the topic for today, as he was sharing a while back, mastering the robotic simulation with ROS2. This is directly linked up to the fourth module, rather fifth module, fourth and fifth module portion. If you remember in the very first day when we were showing you the syllabus of value-added course, so it falls directly with that category. But before going to the topic, which Shomo will definitely put all the efforts to explain it to you. Before that, I must say, Shomo happens to be my student, my uh, alumni from VIT. And currently, Shomo is a researcher at the Robotics Research Center at IIIT Hyderabad, specializing in computer vision, path planning, deep learning, and simulation infrastructure. And on top of it, his research work focuses on bridging the gap between the raw sensor data. I think sensor data we have already discussed uh, quite a lot back when Kathir sir actually discussed the same. So raw sensor data and the autonomous action. He's currently developing MSALT, a multi-sensor annotation platform designed to generate high fidelity ground truth for autonomous system. From engineering end-to-end vision pipelines to implementing 3D deep learning architectures, his expertise lies at the intersection of complex algorithm and robust deployment. He's actively developed. He is actively developing in ROS, Gazebo, and C++ to build systems that can withstand real-world uh, age constraint. On top of it, which is not present over here, that he has actually published quite a bit of papers, research work within a very short period of time and on robotics. And he has been actively participating in most of the robotics based competitions and hardware designs as well. And just a brief small anecdote on him is that the reason why we, or rather I had him in mind, is that in the participant list I can see a lot of young people from second and third years um, coming in for the value added course. So I wanted to give all of you a look and feel of how the career path, or how you can extend your research work on robotics by understanding these concepts and application through different projects, and how you can extend it beyond the academic process of 4 years. So that was one of the reason. And as he's your alumni also, I think it's better to interact with him for any other purpose, which we will come might be at the later stage. And second part is that he has been a very much interested scholar in robotics from the very early stage of his career here in VIT. And from the very first year of when he joined here at VIT, he was very much eager in learning. And today morning, when the Professor Vikas Raut was having the session, if you remember the initial stage when he was explaining the robot, the Fanuc robot which was mounted, and he was trying to explain you through that lab, like what is there in the lab, if you remember. So in the very first stage, Somo was part of that lab as well. He was working actively with that lab. And if you remember, Dr. Kalaidasan, who helped you in the path planning and trajectory session, he was one of his mentor, in fact, in that lab. So all somehow is connected to the overall development and the involvement of how you want to explore throughout the project. And this is some of the outcome, I mean, in terms of Shomo, how he is now going to deliver. So without further delay, with the people around 35 odd people coming in, and mostly will join a bit later, I hand over the session to Shomo. Shomo, you can start presenting, and I think you are you are already presenting, so I think there is no issue with the presentation as
Yeah,
such. Yeah, I
yeah,
think
yes,
we can see your screen.
yeah.
Mm,
So,
yeah,
yeah,
you can start. You can
hello,
start.
sir,
You can start.
audible?
Yeah, you are audible. You are audible. We will take. I hope there will be a lot of queries and questions coming in from people. So I would keep you can post it in the on the chat box if possible, or at the end of the
Yeah.
session, we will try to counter all the questions. I think there should be a lot of questions coming in. So let's see how it goes out. Okay. So the session is all yours. You carry on. And if any doubt, you can just let me know. I'm here.
So I would like to start by thanking Bodhidharma sir by giving a great introduction about myself. So to add upon what Bodhidharma sir said, my name is Soumo Roy, and currently I'm working as a research assistant at the Robotics Research Center at IIIT Hyderabad. To give a background, I also happen to be Bodhidharma sir's property. So I used to work under him for various projects, and also I published a paper under him. So initially I came to IIIT Hyderabad to do my final year bachelor thesis, the 6 months ka internship that you can do in your final semester. Post which I have been working here for a year. So that's about myself. And today my session will be tuned more towards the simulation side of robotics. Why do we need simulation? And how does it bridge the gap between real world systems deployment, like you with a real mobile robot? And along with that, how can it be applied in real world? So I would try to bridge that gap, and that's where my session would start. So the question is, why do we need simulation, right? Yeah. So, many of you guys would have seen on Google or like in the news that generally when there are robots performing various actions, like let's say in this case, the robot is doing a simple pick and place operation. Ideally, in a warehouse like scenario, where the ideal objective of the robot was to pick up a package, and to put it in this conveyor belt. So what happens generally in a warehouses, like you can take example like Amazon, because most of you guys, I'm pretty sure, order, various packages from Amazon. So they are kept in racks like this so that packages can be sorted and then they are put on this conveyor belt, because of which they can be sorted into various trucks and those trucks come and deliver you the particular package in your doorstep. Now the thing is that's where robots come in. Now imagine a human has to continuously carry this box from this point to this point. It's a bit tedious and a repetitive process, right? Any place that is repetitive can be easily automated, and that's where robotics comes in. But you will also observe in this video as I'll play forward that what can be the nuances in running a robot in the real world. So as you can see, the robot is now lifting the box, but as soon as it's going to put it on the conveyor belt, the robot crashes. And now you have to understand that this robot that you see is a very popular digit robot by Agility Robotics. This robot cost close to $1 million. Now imagine what would happen if you crash this particular robot. It's $1 million worth loss, right? In terms of your sensors, in terms of marketing also. Think how would people perceive this standing here if your robot just fails midway? This would not be a good thing for a let's say demonstrator's point of view, and from a scalability point of view where you want to deploy robots in the real world. So the question is, what can we do so that this kind of a scenario does not happen again? This is where simulation comes in. What if we can model this digit robot by Agility Robotics, which is basically a humanoid robot specialized in pick and place operation? What if we can create a digital twin, or you can say a replica of this real robot in a simulation? And with that, create a simulation environment various different tasks so that the robot can know that I have to pick up a parcel and dump it in the right place so that different edge cases or scenarios don't occur. It's kind of, you can say, a matrix in robotics where you can have multiple copies of robots doing different actions like walking, picking up, placing. This can be trained for a long amount of time so that now the robot has learned that, okay, I need to do A, B, C steps to complete my action of lifting a box from one place to another. And this is where simulation comes in. And this is a simulation environment by NVIDIA called an Isaac Sim, where you can simulate humanoid robots to do various walking actions, as you can see here. So today's demo, I would like to show to use a particular platform known as ROS, where it basically stands for robot operating system, where you will need a robot, dual booted Ubuntu system so that we can run various commands for our setup. Like here also, you can follow the robotics documentation, which you can see here. This is the original documentation for robotic operation system. So this will help us to bridge the gap between simulation and reality, which I will show you further in the slides. So this is more setup where you will need mostly the Ubuntu system. I recommend that. So it would be easier for you to set up. So now coming back to the pillars of simulation. So as I told you that now we can have simulation environments through which we can show demonstrations of robots. And for that, we can model various robots. Like here you can see a manipulator arm, which is supposed to do a similar pick and place option. And here you can see a camera. So the camera sees this particular view, as you can see here. And this is a robot that was supposed to pick up, let's say, this particular block. So to kick off this demonstration, I would like to show a demo. So, so this is a demo of a simulation environment that you can see, where you can see this small robot here. This is called a Turtlebot robot. It's a Turtlebot 3 waffle robot that is specially used in simulation environments so that it can be so that you can plan paths and do any kind of autonomous action. Let's say like you want to survey an environment, you want to, let's say, pick up an object and dump it in another place. So this is a rough setup of a simulation environment. Now I'll explain what are these blue lines and these gray lines in the upcoming slides. But this is an environment called Gazebo, which ROS gives you out of the box, or you can install it so that you can easily simulate robots. Like this is a plain environment in which I have a robot. Now I'd like to show you a environment which we will be using today for our demonstration. So this is the environment that we'll be using today for our demo. Now, as you can see that this is a rough environment where you can see our robot present here. And here our basic objective will be to navigate in this area by avoiding these cylinders, where I will demonstrate a basic robotics concepts as Buddhatitya sir had talked about, like let's say path planning and stuff that you would have heard about from your previous lectures, where I'll show you a small demo of us trying to path a plan for this robot to avoid these cylinders and go from point A to point B. So that's more about the demo, and let me go back to my slides. So now I showed you a brief demo of our simulation platform that is going to be Gazebo for our demo. So moving ahead, so what does this Gazebo contain? This Gazebo contains a URDF file. A URDF stands for Universal Robot Description File, which is basically a file that consists of links and joints of the robot. Consider this as my arm. Now imagine this as a robot. So my parts of my hand that you can see, this part, this part, this part, it's called a link. And these particular elbow points in my hand, these are particularly called the joints of the robot. And with this, we have different transformations at different parts of the robot, like over a link, over a joint, so that we can understand the corresponding part of the robot and where it exists in the 3D world. So this is written in a particular format of a file called a Zacro files, which consists the data of these links and trees and URDFs that would go on more towards the robot state. And then we would try to broadcast different kind of transformations for the robots. And this goes into our environment called a gazebo environment, where I'm going to simulate my robot to show you how different components of a simulation are going to bridge in. So now I'd like to show you a demo of a TF, which is basically stands for transformation. Because you might want to know that where the different components of your robots are in this 3D world. And this, as you can see in the robot, you have a odometry frame, which helps the robot know where it is with respect to its links, a map frame. A base link is basically the base of the robot. Like in cars, you have axles, right? In that, similarly in robots, you have a base, which is called a base link. Now I would like to show a demo of how do we see this in a simulation platform. So to do that, I will just launch my simulation again. So here you can see that we can see the transformations. So you might be thinking, where is this coming from? Now we saw this as our simulation platform, right? Where we can see our robot here. But sometimes we might want to visualize the sensor data, like these blue lines are basically coming out from this particular sensor that you see on the top of the robot called a LiDAR sensor. What the sensor does is it shoots laser beams in 360-degree direction so that you can see a map like this. So just to show you, I will increase the size. So you can see these red lines, right? These are coming from your LiDAR sensor. And from this, we will basically make a map of our environment. Now you can see these set of red, blue, green lines. These are basically the transformations corresponding to different parts of the robot coming from a base link. And this particular platform is called RViz. It's basically helps us to visualize any kind of sensor data. Like you can see the LiDAR sensor data. And in future slides, I will also show you how can you visualize camera data on this. Also, the odometry data you would ideally get from a IMU sensor present on the robot. So I will just click this to enable it. Now here I can also disable transformations to just show you that this is the robot, and now we want to know where the robot is in corresponding to this world. And this is where transformations and odometry comes in a very important role to play, where you know where the particular robot is in a particular frame. So that's more about this. We will come back to our slides. So moving on, now how does different components come in? For this, we use Python so that we can write a particular file called a launch file. And this launch file helps us to trigger something called a node where we can tell the particular sensor to share the data on a particular port called serial ports. So serial ports are basically like a USB port that you can say through which you would transfer data from your hardware to, let's say, a simulation or in reality. And this data is sent through a particular channel, which is called a scan topic. I will talk about this in detail in the upcoming slides, but this was just to give you a brief overview of how we are going to bridge things in terms of transformations, which I think would have been covered in the sessions, I presume. So moving ahead, it's not necessary that you only need to visualize a mobile robot on this platform. You can also visualize a manipulator like an arm, like the Fanuc arm that Buddhaditya sir had talked about. Although this is not a Fanuc arm, it's a Kinova arm basically, which is a 7 degree of freedom arm. So using a package called Move It, you can do motion planning and you can take this end point of the manipulator, or you can say the end toolkit, and move this up, down, left, right, and then press this button plan to plan a path for this robot, as I had showed you in the previous slide. Coming back to how would a robot see the world? This is where sensors come in like LiDAR. Because if we need to do any autonomous action for a robot, let's say a pick and place action, a navigation action, we would need a sensor modality to help us navigate in this environment. So think of sensors as a modality like the eyes of a human through which we see the world. There are various kinds of LiDAR sensors. Like the one today we'll be working with is called a 2D LiDAR sensor, ideally an RP LiDAR. So if you can see my camera, here you can see on the top of a robot, I have this RP LiDAR sensor. This is what we'll be also using today for our demos, which I will talk again further in the videos, sorry, in my slides. So now what is the difference? 1D LiDAR will give you one dimension of data. But now from one dimension of data, it might be very hard for us to analyze where things are. So this is where a 2D LiDAR came in. So now we have X position and a Y position of our data. So we have 2D map of our environment, which I will talk about further, that what is a map, why do we need it? But assume that this sensor primarily helps us with that. It also helps us to identify obstacles. Like here, you can see this cone as an object, which is successfully detected by our LiDAR sensor, where you can see here that too that our cylinders from our simulation have been detected here, where you can see this red color points here. That is basically helping us out here. So now moving ahead. So yeah, sorry, before moving ahead. So now two-dimensional data can be very restricted, right? Because think about this cone that you can see here. Chopping a cone at a two-dimension layer so that you know that a cone corresponds to this height. But now you only know what is the obstacle at this height. What you don't know the height of the cone, right? If the cone has a space down, cone has a space up. So that's why 3D LiDAR as a sensor modality comes in. 3D LiDAR gives you 3D information of the environment in terms of X, Y, Z, and the intensity, through which you can see that here you can see a tree, a car, or something. Now, this 3D information is something you can easily get from a 3D LiDAR. So now, what are some other ways we can see objects? Another way of seeing objects is generally through a camera. If you guys have seen, this is a very popular camera called an Intel RealSense camera, which is also s- I which you will frequently see if you work with robotics platforms. So the biggest advantage of a camera is it helps us to see the world in the form of an image. Now, an image, what is an image? An image is a group or a collection of pixels, which gives us a dense information of our environment. But now, what is the advantage of this modality? You can see that it has a limited field of view, right? A camera would have a 60-degree field of view. As humans also, we have a restricted field of view where we can see our environment. That is POV of a camera. Now, think of a human that if you go closer, you can see more area. As you move further away, you see lesser area, also which this sensor can give us a set of images called a depth image, which helps us to know the position of the tree with respect to the frame. This is very useful for the robot as you might want to know the presence of an object in an environment for navigation. And this can be done to a 3D projection to a particular data platform, data modality called point cloud. So this red color data that you see, this can be saved in a .pcd file called a point cloud data file, which would store the corresponding data of the points. Like this point has a particular XYZ coordinate corresponding to it, and a red color of intensity that would tell you that what is the distance of this point, where it is present, and how does it correspond for us. So I would like to show a demo of a camera. So basically you see the robot here, right? This robot also has a camera on top of it. If you can see here, this is a camera whose feed I'll be showing you ahead, where you can see that this camera can see this. So this particular frustum that you see is called a camera frustum that essentially tells you what the camera of the robot is seeing in its environment. So to show you a demo of the camera, I will go here. Now you can see that this ROS tool helps you to visualize different kind of sensor data. Like I can see cameras, I can see the pose, I can see the goal, the odometry, the scan, the laser scan, that is basically the LiDAR sensor data. So here I will select image, and as you can see the description here, I can now, this is basically our, RViz is basically more of a rendering engine. It helps you to render different kinds of data essentially on a common platform. So now I'll click on OK. And now here you can see that we have the corresponding image of what the camera of the robot is essentially able to see. Now, imagine we wanted to see a depth image. So I will go here and add depth cloud. So essentially, the depth would enable you to know where the object is in a particular environment. So basically, you can see different objects like this light gray color, this dark gray color. These can basically tell you the intensities and also the distance at which an object is present at. So moving ahead, um, now where does ROS come in? ROS is basically a robot operating system It's a common bridge platform that helps us to basically connect different sensing modalities like depth cameras, lidars, arms of different robot, and also mobile robot that you can see here. So this is the biggest benefit, and this setup, as I showed you earlier, you can go to the official documentation of robot operating system, and there they will tell you how to install this and a set of demos so that how you can set up a system. So today we'll be working with a autonomous mobile robot kind of a system called a turtle bot, which is basically a differential drive system. So if you can see my camera, this is basically the robot we'll be working with today. This is basically called a turtle bot. So now why do we need ROS? ROS helps us to basically communicate with different sensing modalities. Like here, you can see that there is a particular topic to which you can send a message. Think of it this as humans. As humans, how do we communicate with each other? We need to send a message to another person, right? We do it through speech. We show it through different actions like moving objects. Like let's say I'm moving this robot around. So this is called a message. And you saw the LiDAR sensor, which shoots a point cloud beam. And this can be a message. This is sent to a node. So node is a small set of program that can help to communicate to and fro with a system. So basically, you would send this data, message data over a particular topic, which is called a scan topic in case of the LiDAR sensor. So this is an RP LiDAR sensor, which would give you the 2D point cloud. And this you would send it to another node. Let's say if you want to use a LiDAR to map environment. So this would go to a nav2 node, which I'll talk in the further slides, using which you can map an environment for navigation and communication. Now, topics are like one-way communication, as you can see, where you would have a laser scanner hardware, and this you would send it to another node. Now, what if you want the data back? Because sometimes, as a human, also we want feedback, right? Whether our data has successfully reached a person, has it created an impact on the person or not? This is where services come in, where you can know the state. Let's say the LiDAR has become very hot, and now you need to stop the LiDAR because you don't want your sensors to overheat and stop functioning. So now you can send a command back that, okay, now the temperature is too high, so let's stop. That's where services also comes in. There's a to and fro kind of a communication, more of like publishers and subscribers kind of an architecture for sending data and receiving them data. Where you can say that if you want a please stop message, so you can send it as a message attribute. If you're saying that the temperature is okay, you can again send that as an attribute. So now we will again go back to our demo. So now let's say we want to drive this robot. How can we do that? So you can drive it using, let's say, a joystick, a PlayStation joystick, or using a computer. Today, I will be controlling the robot using a computer to show you an initial demo. And further, we will also try to show you a demo where we can autonomously control robots. So in a demonstration, what we do is we have a joystick. We press various buttons so that we can provide data to the robot to travel. So now if I have to a demo, I will go back to my terminal. I will enter teleoperator. So now you can see that I can use the keys on my keyboard here to control the particular robot. Now, Now I'll press W. So now you can see the robot is moving forward. And this is a differential drive robot where you can see that it has two wheels present. And now you can see I'm easily driving the robot slowly. You can see that front camera is seeing the world. Our LiDAR sensor data also would have updated by now. See, now you know that the robot is here in this environment. You can see its corresponding camera data and also the LiDAR sensor data through which now you can know where your robot is in the particular environment. So I will just drive the robot further to show you how data is updating over time. Now, the question is, you're operating the robot right now. How is it going to control itself? So when I'm pressing any key, you will see that if I bring back my terminal, you can see that I am sending something called a linear velocity. A linear velocity is basically the speed at which the robot is basically moving forward. And when I'm turning left and right, I'm also sending an angular velocity for this robot. As of now, we keep the speed of the robot really low so that for safety and security purpose, so that you don't randomly go and crash into a person. So this is more about the teleoperation demo
Shomo,
where yeah.
Shomo, I have just one advice to you, especially the screen where you are showing the command window. I mean, with four command window kind of demo. If you can
Yeah.
specify which window you are specifying to,
Oh,
I think it will be easier in the because they're all very similar looking. So it's easy for me to point out which window you are in. But I think for general purpose, you can just maybe move around the mouse or mention that which particular window you are in. Yeah, I
yeah.
think that will be the easier way of correct.
So yeah, here I have zoomed in into the window. So this is what I was talking about, where I was controlling the robot to move around using the keys in my keyboard. That is basically this WASD in popularly in our keyboards. If you guys have played any games or racing games or any kind of shooting games, these are commonly the keys that we use even in the simulation gaming platforms to move around. So as I was saying, to repeat my point, we have a linear velocity here, which is more directed towards the straight motion in a linear manner, and angular velocity where we are trying to turn the robot or let's say rotate the robot like this so that you could go further and accelerate. So yeah, moving ahead. Now I would like to show you a real robot. Like here, we have this TurtleBot clone that we have here. This has been made by the people of our lab, a good friend of mine. So I would like to show a demo of this working in the real world, and then I will try to show its translation in simulation. So in our lab, we don't not only make robots, but we also fabricate them from scratch, where you can see that we have different 3D parts that correspond to the robot. And after that, we move forward to print them using a 3D printer. So this is a 3D printer that we have in our lab, using which you can 3D print different components to get started if you guys want to build your own mobile robot. Post which you can see here, you can put a DC motor, which you have seen in small cars, and over that a power bank. And over that, now we have a motor driver, which this is basically an L29 motor driver, which you can see here in the camera. Can just move closer. So this red color thing that you see here is called a motor driver. This is an L29 H-bridge motor driver that helps you to control this differential drive robot, which is basically a two-wheel robot, so that you can control it in terms of left, right, or move it forward, back. Over that, you can see this Arduino board. So this was the L29 motor driver that I was talking about. This helps us to control the DC motors, and we can also send it signal using our own Arduino board. So you can see a demo how you can see these wheels that are spinning and a feedback given by this robot. So this is a low level control board over which we want a high level control board. And this is where the our Raspberry Pi comes in. So using Raspberry Pi, we are going to interface the sensor and send data. It's basically like a mini computer where you can execute commands like a basically a microprocessor so that you can send fine-tuned grained commands using ROS as I talked about to interface with real-life robots. So as you can see, the robot is moving and at the top you have this LiDAR sensor that's rotating, shooting laser beam around continuously. So this you can see our robot that's basically operating in our environment. So with this, I will go back to my slides. Now, what if, now how do we basically navigate in an environment? This is where maps come in. The biggest advantage of that the LiDAR sensor gives us is the ability to map environments. So basically, you can create a map in the environment by moving your robot around, and the laser sensor would essentially help you to create a map like this. So for example of this environment, I have made the robot move around and create a map. So I'll just show that. So this is a map that I have made of my environment. I'll just zoom in. By basically driving the robot around. This is called an OGM, that is an occupancy grid map, where you can see various cells, white and black. So the white corresponds to free area where the robot can traverse. The gray area signifies the area that has still not been explored by the robot. The black color indicates that this is an obstacle which needs to be avoided. So this is where mapping comes into the play. Why do we need to map environments? Because it's like more of a chicken and an egg problem where if you know where the robot is in the location, you would need a map. And if you want a map of the environment, you need to know where the robot is located. This is called SLAM, that is simultaneous localization and mapping. So here I know where the robot is in this environment. So now the question is, how do I know where the robot is in another environment? So for this, I will just show a demo again. So here you can see that I have loaded the map in my environment that you can see here. So I will just go back to my slides. So first I'll give a background of how we are going to go for an autonomous navigation of this robot, basically using the nav2 stack provided by ROS. So ROS gives this nav2 stack where robots can be controlled for an autonomous action of moving from point A to point B, where basically what the stack consists of is a waypoint follower. What is a waypoint follower? Now, let's say there are points in the map where you want a robot to traverse and follow. So, to create a smooth path, what you do is you create a set of intermediate points. This set of intermediate points is called a waypoint, which the robot is going to follow to achieve its goal from, let's say, moving from point A to point B. Now, this is very important for autonomous systems where you might have some kind of a language command, say, any command that is generally a coordinate on a map that you particularly want the robot to. So this consists of a behavior tree, which is basically a set of different states of a robot. Like let's say you want the robot to go front, back, brake, go to a charging dock to charge by itself. Like how you have seen this robot vacuum cleaners that generally go around your environment, map the environment, and also when it's running low on charge, it would go back to its docking station. And these states are handled by this behavior tree where you have a control server which has this local cost map. So I will just show a demo of that again. So now you can see that I am giving a 2D pose estimation of our environment, where you can see that currently the sensors are finding it difficult to align. Now, this is where we are going to apply something called a AMCL algorithm so that we can figure out the exact alignment of the robot. So just to this. So here you see that I've um, again created my environment from scratch here so that we can start our autonomous navigation again. So I will just load this again. Sorry. So basically, I would like to also dissect the robotics package and tell you what it contains. So basically, I'm in a Turtlebot workspace that you can see here. Now, if I do ls, that basically stands for list all the components. We have different components like the source directory, a build directory, a log directory. So what we basically do is we build or compile our systems. So basically, if your work is C++, we compile the code using a compiler called G++, which you have generally seen, right? Similarly, in robotics also, we compile our code in ROS2 using call point build. So I'm going to compile my code to show you a demo. So why are we compiling code? Now you can see different components of the TotalBot robot, like the messages I told you earlier, the description of the robot where you were able to see the black color of the robot. You can see the simulation library called the gazebo, a cartographer library. Navigation library is what I'm going to talk about right now. where we are going to do this autonomous navigation, but we can also navigate the robot using teleoperation, that is using a controller to move it around. And also the simulation package that I've been using to show demos of this robot. So, so what you need to do is once you build your packages, you need to tell which packages needs to be used. And in my case, I'm telling my system that, okay, follow the package here to launch. So with that, we will launch our navigation system. So now coming back, I am going to give a 2D pose estimate. So now you see our robot has closely aligned to basically where the robot was supposed to be present in this environment. And this is called a localization of a robot so that a robot knows where it is in the particular environment. And this is done using a particular algorithm called adaptive Monte Carlo localization, called AMCL, so that it's basically a particle filter that helps to make its estimate over where it is over the particular environment. So now you can see this violetish shade, right, of a small window. So, oh, sorry, before that, you saw this green color particles, right? These come from the AMCL window. And now that the robot knows where it is, our particles. Sorry, was there a question? Yeah,
No, Zomo,
so
nothing.
yeah, so as you can see, the particle filter has converged and all the green points have vanished. Now you can see that we have a cost map. So this, sorry, before that, this black and white environment that you see is called a map. So you can see that I'm disabling the map and now I'm enabling it again. So this background that you can see that I'm flickering is called a global planner, where the robot knows that this is the entire environment through which I need to navigate through. And over that, this particular purple window that I'm toggling is called a local planner or a controller or cost map, which estimates a cost of where the robot can go through and where it cannot. So this light blue color area is called an inflation layer, so that this knows tells different cost of the robot so that it knows where it can traverse through in an area. We create this inflation layers generally for safety for a robot so that it can navigate easily to an environment. So different colors here signify different cost, which is basically in layman terms of probability distribution of the free space area and a occupied area so that the robot can easily traverse through. So now what we will try to do is, now I'm going to give a goal to the robot to go to another place. Let's say I give a goal here to go to this point. Now you can see that the robot is going all by itself autonomously. And this is the power of the Nav2 platform, which allows you to autonomously control robots to go from one point to another. So now you can see the particle filter or the AMCL is slowly converging. Now let's also see the map, sorry, the camera feed and what it's seeing. So you can see that the camera is seeing this, which is pretty true, right? Because the robot is facing this direction. Now let's also visualize the different sensors that we were using. So I will just go back to my hardware's window. Now let's say I want to see my point cloud data. So we will go back, load this. And now we can see these red color lines, which basically is my point cloud data that you can see here. I don't know if it's visible, but yeah. So here, see. Now let's try to give another goal. Now you can see how the camera images is changing, how the point clouds are changing, how the cost map is changing, which is guiding the robot more easily. Now a robot needs to find an optimal path to go through these narrow areas. So this is where nav2 comes in, and it helps you to provide smoother and precise paths for robots to traverse through. You can see here the robot is going to the environment again. So what did I basically do? What I started with is I gave a goal pose. I gave this goal pose that was basically through this nav2 goal that you can see here. Now this nav2 goal is basically translated as the command velocity, which I told you earlier, right, through my slides, where that this is basically a topic that's just going to send the velocity commands. These go to the ROS2 controller, and this goes to the motors of the robot so that now the robot can easily navigate and traverse through environments. So now if you want to learn more about this platform, you can also visit the NAV2 documentation where they will explain you how to localize, move around in an environment. Basically, the demo I've followed to explain the basics. Now let's dissect NAV2 in a little bit depth before we move further. So what did I show you? I showed you a local cost map, which is basically this purple color small temporal window that you can see. This was basically the local cost map. This global cost map was this background environment that I showed you by clicking on it. I'll show it to you again. So this is the global cost map. Now the question comes is what if you want to understand the behavior of robots, right? Like sometimes if you give unfeasible paths for the robot, there might be issues for the robot to converge around, right? So let's try to do something. So let's try to give the whole view. Now you see the robot is traversing extremely close, because of which now it has collided. So this is the condition where I've given an infeasible path for the robot and now the robot is stuck. So this is where recovery behavior comes in, that, okay, if you know that there's a wrong path or a wrong scenario plan, you need to model a behavior so that it can go back originally, and because of which we calculate something called a footprint of a robot so that we can analyze its behavior. We also have something called a smoothing server, because as you saw the paths earlier, which were relatively smooth, this is done using the smoothing server so that you can have a decent profile of a linear velocity for the robot to easily traverse through, right? Imagine like this as a ABS that you have in a car, which basically stands for anti-braking systems. You want a smooth trajectory, right? When a car overtakes, you do not want a hard trajectory of a robot suddenly turning, right? It would cause the damage to your various like motors of the robot if I suddenly turn the robot. And a life cycle manager that helps to manage the entire life cycle of this. So this is where the importance of transformations, the map that I talked about, the sensor data comes in, which generally goes into this nav2 stack over a velocity smoother, so that we can also avoid collision, plan a path, and send this to this robot base that I was telling you about. So here this transformations you can see is basically coming from this TF, and you can see this arrows basically of the AMCL particle swarm, and this is mostly trying to correspond to the base of the robot. So now I would like to talk about why simulation. People often do research on robotics. Even I myself am doing research on robotics, where most of the people tend to reinvent the wheel and do a research over it. This is where simulation comes in so that we can plan ahead of time to prevent collisions. It's also, you can think of it as a safety check for robots so that, before deploying any algorithm in a real world, you might want to test this out on robots for safety for humans so that, you don't want a robot to collide with another human, right? As in the demo that I showed you earlier, where the robot fell because of a collision or a orientation problem. So I would like to switch gears and go a little bit towards the research aspect. So I've worked with Buddhaditya sir in VIT, where I worked on a simulation of a robot. Basically, this is a robotic arm that's trying to do this assistive action of feeding and drinking using reinforcement learning algorithms for planning the path so that the robot can assist the human to have food. Now, these are very common robots over this OpenAI Gym platform, which is another simulation platforms, so that we can test algorithms before trying it out on real humans. Imagine if such a scenario where you accidentally hit the human. This is where you know that you can learn from edge cases and try to avoid them. Now, directly testing these algorithms on humans can be very dangerous, right? This is where our research came in, where you can see that the robot is trying to pick up food from the bowl and then feed the person. So these are popular assistive robots. Like this is a Baxter, this is a Sawyer robot, which are very frequently used for assistive actions and a very trending topic. If you have seen NVIDIA's GTC event, Jensen Huang also showed a simulation of robots doing actions in that Isaac Sim environment. So that this is where we are trying to bridge the gap between having machine learning and deep learning algorithms in simulation into the real world to do useful actions instead of just having black box. So one of the things I work in this lab is an autonomous wheelchair where basically this wheelchair is using a generative AI algorithm to plan a path from point A to point B. As you can see that you might want the robot to avoid humans and not collide with it midway, right? Now the question is, how can we leverage the simulation, power of simulation to avoid various scenarios? Now you will see a scenario of a person lifting a box and trying to put it, where you can see this unseen obstacle that has been put. Normally, a robot would collide with the obstacle because you have not seen a sudden obstacle that has been kept. Now the map would also change over time, right? If you suddenly keep an obstacle. So these are new areas of research that we are trying to bridge the gap towards. So here also you can see this robot has this 2D LiDAR sensor where this obstacle has not been seen, but still the robot navigates through it successfully. But you can see that the robot also got confused midway. The question is, how can we avoid scenarios like this? So this is where uh, the we also leverage the power of simulation in our lab, where we initially train it in simulation, where you can see the same turtle bot that is trying to move through a dense scenario of people that are continuously moving, where I've given a goal, where there is a goal post that has been given for the robot by one of my colleagues in the lab, where you can see this robot trying to use a diffusion based path planning model or a generative AI path planning model so that it can move around and reach this red point, which is basically the end goal. Now you can see this red color points on a map. These correspond to the laser scan message, or you can see the point cloud that you are getting from this 2D LiDAR sensor from this robot. As you can see, it's trying to successfully navigate and avoid people in the environment. You see, this is also a gazebo simulation platform and the same ROS platform too that we have used for basically visualizing sensor data and to also navigate a real world deployment. So you can see that initially it's trying to plan a smaller path, generate smaller waypoints, as you can see here, to reach its end goals. So now we are creating a sample of paths, a diverse scenarios, which a robot can traverse through so that you don't collide with the person and reach your destination in a easy manner. So yeah, with this, I come to the end of my presentation. And now I am open for questions. Before I move on to Q&A, I followed a documentation of TurtleBot 3 on this web page where you can learn about how to set up your system, how to navigate through a system, right? How to do a frequent um, operation of robots like the SLAM that I talked about, that is the simultaneous localization and mapping, the navigation, the simulation, the manipulation, how we made the robot move around, autonomous driving using nav2, where we drove the robot around in an environment. So with this, I leave the forum open for questions. Any questions? Anything? Hello, am I audible?
All right. Yeah. You are audible. You are audible.
Hello. I have a
Participants, anyone having
hello.
question, please.
Yes, sir. I wanted to
Uh,
ask that which sensors are we using for localization in the turtle ward?
we are using this LiDAR sensor. If you can see my camera here, feed this sensor that you can see here, right in top, this black color sensor. This is called a
Uh,
2D LiDAR sensor, called an RP LiDAR. Using that, we localize.
okay, thank you.
Does that answer your question?
Yes, sir.
Yeah,
Hello?
so I have a question too. So,
Yeah. Hi.
which Raspberry Pi have you used? Like, is it
Which?
uh, Raspberry Pi? Raspberry Pi. Is it just Model
Oh,
4
this correct. We are using model 4B. So
and
it's
4 GB
very
RAM
good.
will run?
I mean, we are just running normal nav2 stack, so that works out. If you run
It
something
works.
very heavy, we have Jetson boards in our lab on which we run heavier algorithms.
Uh, I believe that the LiDAR sensor is very costly. This is actually my dream project.
Yeah.
What are all the softwares you've used? So,
So in terms of software, as I told you in my slides, I use this robot operating system, ROS. This is basically a software platform that helps us to bridge the gaps of the robot. So this is one I've used. Another thing I've used is this nav2 software stack for doing
uh,
the navigation. I've also used Gazebo as a simulation platform. If I just go back, this is, oh, sorry. Yeah, this Gazebo window. This is also another simulation software platform that I've used to show my demos.
so all of these are
And
free or um,
yeah, all of these are free. These are all called open source packages
okay,
where you can go
great.
to a place called GitHub to download them. So
Hmm.
I would just like to show you one demo since you asked the question on this, right? So you can go to GitHub, type this. So this is the complete open source software of at least the Turtlebot that I have used. This is for the motor drivers like that. Most of them are totally free. Like this Turtlebot driver, I have also taken from the GitHub itself. So I'll just show you the
Shivu,
exact one.
can you paste that in the comment chat? Can you paste
Yeah.
the link in the chat?
So I have used this package for simulating this Turtlebot robot that you can see. Here I am working on ROS2 Humble. This is basically on Ubuntu 22. I'll also paste the links of ROS2. This is for the ROS2. This
It
is
runs
for
on Windows
Lab2.
also, right?
Yes, it runs on Windows, but ideally I would suggest to use Ubuntu because you would have a good support in terms of the software packages. Like I would recommend that.
Okay.
So why are we using ROS2? Like, what's the difference?
So basically, you mean ROS2 or in comparison with any other package?
So like it's showing ROS1 and ROS2, right? So you
Correct.
just said we are using ROS2.
Correct. So basically, the thing is in ROS1, you have reached the end of life support. What it means is if you use an Android or let's say a iOS smartphone, like let's say an iPhone, you would have software support for it, right? For every operating system, right?
Yes.
So ROS1 support has been stopped, which is the last version was in Naitik, which was stopped last year in the month of May. So that is where we have moved on to ROS2. That's one reason. Second reason why we use ROS2 is because of the improved communication using something called a data distribution service. Because there were many problems in the communication of robots using ROS1. So there was a need for a centralized system for communication where DDS and things were implemented, and that is where ROS2 came in because there were many security flaws of so in the robot where in ROS1, if you just SSH, if you guys have worked with Raspberry Pi, right? So how we connect to a Raspberry Pi from a remote system? We connect to the same Wi-Fi. We know the IP address of this Raspberry Pi, and we can ping it and do SSH to log in into this Raspberry Pi board, right? So now I have access to all the data of this robot. So there is no security, right? Imagine you have to deploy this robot in the border for surveillance purpose or security purposes. So I can easily log into the robot, see all the topics, see all the sensor data. So it's a security risk, right? So to have a centralized system of safety and security, better communication, we moved on to ROS2. Does that answer your question? Or
Yes, sir. Thank you so much.
yeah, so it's more of a latest software with more packages support. Is that you don't want to go back to an old software, right? Because the old software has stopped its support from last year, May, I believe. So that's why even I shifted my entire demo to ROS2 because I thought ROS1 would be out of date. So we are also migrating our entire stack, like the wheelchair that you saw, that also operates entirely on ROS2 now. So yeah, any other questions?
I
I
wanted
think
to
one
ask,
question I would ask. Oh, I'm sorry. I'm sorry. Please go ahead. Please go ahead.
yes, sir. So I
Ashit.
wanted to ask if, like, we mostly use Python, right, for robotics operations?
Yes, Python, because Python is easier to write and easier to understand, and there's a good library support for it. But sometimes we want a good speed to run our program and we want quick inference time for our robots. Like let's say I don't want any kind of latency that comes with Python. That is where we move on to C++ so that we can have a better speed and memory optimizations for our code.
Okay, so let's suppose there is so much library support for Python. So if we're shifting to C++,
Correct.
then we'll face those difficulties, right?
Yeah, difficulties will be there.
Okay.
But ideally, it's the other way around. The support for C++ is better than Python because even if you see the newer ROS versions like the Jazzy version, most of its library supports are in C++ because now speed has become a very important commodity for people. So things are there. And thus coming to the second part of your question, I think you can write C++ Python bindings so that you can have this portability of using your C++ bindings in Python for your library support and those things. So yeah, software is becoming more modular over time, I would say.
Okay. Okay.
Does that answer your question?
Yeah, yeah, yeah. Thank you.
So Python is more like a scripting language, but if you want more in terms of memory optimized language, we move more to embedded C, C++ and those platforms.
Oh, okay, okay.
Like in fact, today I was processing LiDAR data and I just realized that in Python, it took me like 1 minute to process like 3000 frames of LiDAR data. And I wrote the same script using C++ for an experimentation. It barely took me 1 to 2 seconds to process 3000 point cloud data. So speed really matters now.
Okay. Oh, I just had this doubt because uh, like most of the robotics operations they generally use Python, but since C++ is faster, that's why I asked this question.
Correct. Okay. Yes, sir, Buddha. Sir, you had a question.
Yeah, I was listening to the conversation. I think that itself sums up the session itself. Like it was very informative and well demonstrated with all the example. That's first thing. Uh, Two specific thing as an instructor, instructor's point of view, I would say, because this is I don't think that is the right forum to discuss anything other than this. One thing is, as a robotics engineer and being in projects for some time now, uh, what do you feel about the bridging of the work that you are doing right now, or the experimentation that you are doing right now with the demands of the industry? Have you ever, or in your lab, or where you are actually collaborating with, are they working on some problem statement given from industry, or the one that you have shown just like now is part of just a standalone project? That's first question. That is the first question. Second thing is that if suppose from the student's point of view, they want to venture out in Indian context, about some internships or internship opportunities, or working in future in robotics, what do you think as a roadmap? If you can give that input also.
So we'll break this question down into first question and the second one. To answer the first question, you can see this wheelchair here, right? This wheelchair funded by the Department of Science and Technology. It's a funded project where we are basically trying to deploy this wheelchair in, an academic setting, like in our IIIT Hyderabad campus, to help students like with a ligament tear or something to help them go from the hospital setting to a classroom setting. That's one kind of a deployment. We have also deployed this in this AIG hospitals in this Hyderabad, where this wheelchair is essentially as a platform to move people from the patient cabin to an ICU cabin autonomously. Also in airports, there are long stretch where you need to walk on. We are also trying to deploy where a person would just program a robot, give an end goal, and it would take you through the entire terminal of the airport to roam from, let's say, A goal point to B goal point. So this is bridging the gap between a robot built in a lab to its real deployment scenario in the world. So that's first question. Is there any follow-ups, or I'll move on to second?
No, see, no, I got the idea. I mean, this is definitely a requirement, but in terms of, I'm saying like, when you tested, I mean, in your
Correct.
case or whatever you have done as the project, what are the bottleneck problems were associated in terms of the project and also in terms of the situation of the robot itself? Because in what I understand from the robotics deployment in Indian
Correct.
environment, it's a very narrow deployment, like deployment that ideally it happens because we are a country where we are more labor oriented country. So what are the challenges you faced while you proposed such an idea to a condition that we will automate the things? Is there any bottleneck problem that you came up with?
So I would like to show you one. So
Mm-hmm.
if you can see on the screen,
Mm-hmm.
one thing is, what do you do when there are unseen static obstacles? Let's say randomly you have kept something. In my
Mm-hmm.
map, I don't have it, right? As I showed
Mm-hmm.
you. Now the problem is when you keep this unseen static obstacle, just observe what happens. The robot got confused. Did you observe that the robot just bent like this and came like this? This is basically a trigger of a recovery behavior of this wheelchair. So path planning is still not very robust, I would say. I'll just play it again to show you. So confusions do exist where when the wheelchair is traversing through a path, it can suddenly get confused for a minute and so,
Mm-hmm.
and then try to recalibrate and come back to the spot to move ahead. Now, this is okay in the academic scenario. What if it suddenly loses itself in airport? It would be potentially very dangerous, right? Your wheelchair would
Mm-hmm.
potentially start spinning. So these are some challenges.
Okay.
I mean, technically, I could have shown videos of spinning, but yeah, something hilarious to watch.
Mm-hmm. Yeah. And
So,
regarding the second part of the
correct.
question.
So, regarding the second part of the question, I would suggest you guys to start making projects in robotics because ideally, I have seen companies ask for projects now. Like this is one of the projects that you can see one of my lab mates have basically built, and he's doing pretty well now in life. So you can build small robots like this, like Turtlebot. I basically showed you this Turtlebot's website, right? So they have complete instructions also that how can you build this robot from scratch and do things with it, There is this hardware assembly, if you can see here on my screen. You can 3D print your parts, you can assemble your parts, and you can build small robots like this. If you want to do simulation, you can do like smaller projects of path planning using nav2 or make your own path planners algorithms. Like I had worked under Budaditya sir, where we had also worked on path planning using reinforcement learning algorithms. So you can have simulation projects like this, have YouTube videos or demos to show your interviewers that, okay, this is what I've done. You should have deep clarity and in-depth knowledge of your projects that why have you done X approach? And in terms of system level thinking that, okay, how are you going to design, let's say, an entire path planning scenario for a robot? So you should think in terms of systems that if somebody tells me to develop a robot tomorrow, how am I going to build it from scratch for the particular person? Because if you go for an internship or let's say to work in a startup or a company, they would have different problem statements for the robot. And the question is you need to think in systems that, let's say in perceptions, if I have to move aside from this LiDAR to a camera module, how would I do that? Now I cannot get odometry from LiDAR. So I can get odometry now from camera using VIO. This is basically like visual inertial odometry, like that. So you need to know in terms of trade-offs and systems, why you are going to take X approach, why you're going to take a Y approach. And in terms of applying to internships, I think LinkedIn is one of the best places to look for them. And one approach that I followed, I don't know if it was a nice thing to do, was to cold email people. So I've like rigorously searched on LinkedIn that what are the robotics jobs, who are the people offering. So I have figured out their email ID and I have vigorously mailed people. I think for my first internship, I mailed close to 150 people, close to, and I heard back from three and I got offers from two. So ideally, even when I have done like research internships at like IIT Kanpur and even here at IIIT, I've essentially cold mailed people. But essentially, cold mail as an approach only works when you have proof of work. So start building your proof of work with smaller projects as a demonstration, and then you can start, approaching people like managers or people working in companies, asking them that who is in charge working in, let's say, the path planning in the company. Can I interact with them, schedule an interview, tell that how can you add value for them using your projects?
Do you need
So
an
this can be
SOP
one
for
way.
that? Do you need an SOP like we usually up when we
Like
apply for something like that?
I required SOPs for research internships, not for companies. But nowadays I'm seeing few companies like Volvo recently I saw, they are asking for this cover letter or a kind of an SOP of your current plans, your future plans, and what interests you.
And the SOP, in the SOP, you should be mentioning about your, I mean, you should have a very foolproof
Correct,
project experience that you need to mention, right?
correct, correct. So you need to demonstrate your proof of work.
Hmm. Okay, so is there any other questions from anyone? I think
So I think this one
Sunit
on the
Ghosh, I
chat.
think. Yeah, yeah, yeah.
Yeah, even I cold mailed and like I actually got an internship in my second year of BTech and that to a paid one. So that was like
I
pretty
think that
good.
was
And
in
I
Pune,
could have,
right? That one in Pune.
I went in Pune.
Unbox, is it?
I
So you
applied
got
to
paid.
LinkedIn for that, but yeah,
You got
sorry.
paid for the internship. Me.
Yes.
Oh wow.
Yeah, so I think this is
So
a very
I've
good uh,
in
response from your
terms,
side, I would say, because very honest reply that you gave that we have to be a bit proactive and just cold mail people and just wait. In a way, you make them a bit bothered with recurring mail that you have been sending them until after certain
yeah,
period they will be they will be reluctant of not responding, but just to communicate back to you. I think that is a good way. I mean, you need to be a bit patient, but I think that is the only way I feel.
yes.
Even in
Uh,
nowadays.
as a second year student, I mean, what is easier to get is ideally a research internship because
Mm.
professors don't need to pay you for summer research internships. So you can try cold mailing professors in IITs, NITs. I think I had emailed almost all the robotics professors in the
Mm-hmm.
top seven IITs and even NITs and IIITs. So I heard back from a few of them. So, I mean, that might be easier. Generally, companies can be a little bit hard to get into because companies would check a lot of things before
So if they
bringing
get
you
in
on
touch,
board.
if our participants in this group or anyone wants to come back to you, is it okay? for you? Will you be able to assist them?
Yes, sir. Oh, this is a really good question on the chat. Now, ideally, I did not have very good academic credentials. I had a CGPA below 9. Now, what helped me was my past experience and my publication. I had published a paper with Muralidhya sir before going for a research internship. So
I think two
that was
papers. I
in,
think two
yeah,
papers.
2 papers.
Two papers. Yeah.
So it was basically on a smart dustbin. So that's where I was able to sell myself well, that other my competitors don't have a paper, but I do come with significant research experience. But ideally, you should have good academic credentials for at least the summer research programs at IITs. Like I went for a summer research program at IIT Kanpur called Surge program. Essentially, the document says that you're supposed to have a good CGPA as per their website. But when I got in also, I realized that I was the very few people who got in with a low CGPA. So yeah, academic credentials might be checked. I mean, it highly depends on the professor. If he's like a very academic oriented person, he may ask. But don't have a very low CGPA because then the professor or the PhD scholar who would take your interview there would ask that why do you have such a low CGPA? And you will have to compensate that. So in my case, I was able to compensate that with my proof of work. So you need to think about that aspect well.
All right. Fair enough. I think participants amongst them are is a mixed bag. There are people from external institutes as well, and some of them are in fourth years, third years, and all. But I think they got a very good exposure from working individual in robotics, and with whom they might connect a bit more compared to any other. And it was really a very good eye opener, I guess, for them, because it was very much relevant to the syllabus that we are following. Unfortunately, I haven't shared you the syllabus, but fortunately you have covered some of the topics which were there in the main syllabus. So
Yeah.
yeah, so I think that sums up the importance of it. And in fact, some of the sensor in terms of the LiDAR or any of the sensor setting that you were showing, those were also taken care of by in the theory in one of the module. In fact, the transformations was also done as in terms of the DH and all. So those theoretical understanding also were taught to them. So they might have understood the impact of where the concept which you were talking about, that the base of the concept is important, and how it is reciprocating in the software as well as after you implement it in hardware as well. So I think that was a very good closed loop and a good bit of discussion going. I uh, I don't think there is any further question. I can't see any question as of now. What you can do
Even
is, tell
even
me.
if there are further questions, you can contact me on LinkedIn or email ID. I would
Yeah,
be
I think
happy
that is
to
already
respond to
shared.
questions.
I mean,
Yeah.
that is also shared. Even this whole recording, we will be sharing with the participants, so that at least some of them can continue the good work that you are also doing, and maybe
Mm.
collaborate with you or any of the others, and we can have a very sustainable environment in terms of the robotics development in campus. So with that, I would thank you particularly for accepting an invitation to join in on a Saturday, being a week off, I guess. I don't know whether there is a week
No,
off,
there is no pickup.
but I think for the researchers, there is no week off, it seems. So it's a regular thing. But for us also, it's a quite a good privilege for me to come back to you again and again, and to enlighten us, enlighten me as well with your progress that you are making. And I guess the resources that you have shared, the inputs that you have given, will definitely help the participants in coming future. And they will definitely look into all these avenues in order to boost their career opportunity, I would say, in robotics, and maybe with further studies and all. So I thank you on behalf of everyone here, as well as Dr. Moinul sir, my coordinator, as well as Dr. Kativelan sir. All together, all of us, thank you for your time. And with that, we come to the end of this session. I thank the participant for your active participation and involvement. We'll get back to you in the next class. With that, we can sign off. Thank you and good night.